Hello, my name is Jose Miguel Armijo. I'm part of Universal Projects. And today we're going to talk about the series of prototypes we did for NASA's Centennial Challenge, Mars 3D Print Habitat. This series name is NEST, Nested 3D Print Settlement Technology. When I was in high school, I lived in the north, in Iquique at the Atacama Desert. My father and I used to drive often to the south along the coastline, and sometimes we wonder in those drives how great it could be in the future to see how cities and settlements will emerge under these harsh conditions, but in this beautiful and amazing landscape. 20 years into the future, and Aníbal Fuentes, one of my dearest friends and colleagues, invited me to participate in 3D Printer Habitat Challenge. This contest wants to include the public and private sectors in the process of accelerate and advance space technology and seek small business, entrepreneurs and students to join the space industry. There are different challenge categories a part of our 3D print habitat. There is the Cube Quest for small satellites for advanced operation near and beyond the moon. The space robotic is to control the Robonaut 5. It's a humanoid robot in a simulated NASA mission. The Vascular Tissue Challenge. The aim is to provide the suits and prosthetics functional to protect human beings in deep space. We separate the assignment brief into three different array of constraints. First, all the constraints revolving around the journey, then all the constraints of the environment, Mars, and final all the inhabitation life sustainability constraints, how to build the inhabitation. In general, the journey to Mars will be one of the most ambitious processes of humankind. It will require our best creative minds to create new technology with our available science, but also will require courage to go further away and explore deep space. Furthermore, this journey will also address current problems we have here on Earth regarding the scarcity and waste in extreme environments. The assignment constraints related to the journey can be separated into three different aspects. First, the travel itself, then the material that we will use during that period of time, and finally the resources that we will use for that long journey. The travel itself will be a long one, from 5 to 10 months to get there. It will require 3 chips, and we need to use the alignment window that each 2 years is placed between the Earth and Mars. The first rocket will be used to go from the surroundings of the Earth to aboard a second, more larger chip that will be used to go into deep space and to Mars, and we will use another landing vehicle to go into the surface. Probably we'll use a number of steps in the way, like the International Space Station or Moon, or the moon of Phobos in Mars. The NASA assignment says that it will be in 2035, and we will stay there for 18 months. So we can in advance deliver parts, machines, or resources prior to 2035. Adding to the uncertainty related to the mission, from how processes and materials will behave in deep space and Mars, we need to address the high cost of sending material. For each kilogram today, we will spend $22,000. For the settlement, we need to think how to reuse materials, parts, and waste from the 10-month journey. This has already been tested. In the NASA Centennial Challenge Phase 2, some teams worked to find ways to 3D print structural parts using recyclables and simulated Martian soil. In words of Rob Mueller, senior technologist for advanced project development at the Swamp Works Laboratory at NASA's Kennedy Space Center. Thermoplastic, which are the plastic polymers that become moldable when heated, could be obtained from discarded packaging material or even created in Mars using the carbon dioxide atmosphere and hydrogen from water found in the soil. Such concrete materials could also have application on Earth while using discarded plastic trash. Different kinds of resources will be used in this journey to Mars. First, we will use mostly liquid fuel for propelling the rockets from the Earth to the upper atmosphere. Once we get into space, we will change to a large, big vessel, what we will use in solar and nuclear energy. These two energies will be the ones we will be using to travel and deploy in surface, solar and nuclear. Most of the water for the travel will be bring from Earth, and we will need to recycle, but we can also, in the way over there, we can mining some water from the moon, or once we get there, we can also find from the water that is in the soil. And finally, if we think about the food, most of the food we will be using over there will be carried, like 80%, but we will use semi-prepared autonomous systems to grow, and that will represent 20% of all the food that we eat. If we develop more technology, that percentage could grow to even 50 or 60%. To arrive in Mars is to address a lot of different challenges and problems, but once we get there, we will face a lot more. How human beings will endure under those alien conditions? I think with technology and design, we can use them to create new type of inhabitation. And this milestone can be also used here on Earth to secure our countries with new type of construction. These alien constraints that we need to think about are how we get the water, what is the temperature in this desert-like environment, what's the atmosphere composition, how is time related to Earth, how the lack of magnetic field will impact us, and how the regolith can be used to grow or construct our settlement. One of the main resources we need to address once we get there is water. Water will be in form of ice in the North Pole. Another way to find water in Mars is looking for the galleys. Galleys are seasonal marks on the soil that can be related to CO2 or HO2 that emanates to the surface before it melts and evaporates. The hypothesis here is the Martian soil is like a sponge full with water, and when there are different seasons like summer or winter, this sponge releases some of the water. Another way that we could harvest some water is through the atmosphere, the thin atmosphere that is in Mars. But that's something that we need to test first. Temperature in Mars is variable, but roughly we can say that it's from minus 127 degrees to 20, with an average of 1 or 2 degrees above zero. This oscillation can be happening in one day. In general, we need to think this surface as a much colder than the Earth. The lack of magnetic field could be extremely dangerous because of the radiation from the sun that impacts directly to the surface. So the radiation shield for the human being needs to be addressed both from the shelter and the spacesuits. The atmosphere is mostly of CO2, 96%, and compared to Earth, roughly 0.6% of that atmosphere you can find at sea level. Most of this atmosphere is being swept away by the solar wind. There is also dust storms. This will not be harmful to human beings, but to the drones and robots operating in place. A shelter or a warehouse to keep proper maintenance for them will be needed. The regolith present on the surface of Mars will be the great use for the construction of our settlement. But also in the future, if we want to sustain a colony over there, we need to learn how to grow our food in that peculiar soil. For the construction, we have at our disposal sand that we can transform into glass and different types of basalt rock as volcanic pebbles that is an indicator of rivers and also we can find nickel meteorites. Different materials that we can use to do and produce different tools. The high presence of iron oxide in the atmosphere gives Mars his signature red. On the other hand, the regolith on Mars can be used to grow food. We have all the minerals we need for that, but also we have some minerals that could be harmful potentially for human beings, like lead or mercury. Further technology needs to be done to get rid of the harmful minerals and take advantage of the natural soil and features on Mars. One of them is the water molecules that can be used to grow pools of algae. These pools can be used to grow food and also to shield radiation. The first human that will get to Mars will have already some or most of the settlement built. They will get there to inhabit and deploy some systems, but most of the settlement will be already built. The inhabitation main objective is to provide life sustainability to explorers. As an alternative objective, this will be the first settlement of human beings in Mars, so it will be a stepping stone for next generations to come. According to NASA assignment, we are going to build for scientists, biologists, geologists, engineers and pilots. They will be 4 explorers that will work and live for 18 months in the surface of Mars. They will arrive in great ideal health conditions, and they will be joined by a swarm of droids and robots to operate. The settlement's assignment requires for atmospheric stabilization. We understand this as different kind of atmospheric protection. The most important is to provide oxygen to human beings, but also to provide the atmospheric pressure that we're used to in Earth for using water and grow vegetables. The bottom line is to provide shelter for normal activities for a year, and we need to accomplish that at least in 93 square meters. If we accomplish this settlement, it will be the first man-made architecture in another planet. As a requirement from the assignment is to select a Martian site. And we select Valles Marineris because there is a private ground for exploration and protection in Mars. Valles Marineris is a 2,000 kilometers long canyon in Mars, almost half of Chile. It presents best conditions for establishing the settlement, with high solar radiation to produce energy and a great quantity of relevant geological sites for resource extraction and exploration. The ground altitudes down to 4,000 meters could help providing a slightly denser atmosphere, and the abundance of galleys are indicators of liquid water that may be beneath the surface. Within this large region, the settlement will be located over a moderately elevated terrain feature on the west edge of the Candor Chaos. We could use it as a way to orient future explorers in case of failure system, and a way to be between the geographic characteristics of the bottom versus the typical surface of Mars. We suggest as a test site on Earth the area of the Atacama Desert in Chile. Due to this similarity to the Martian surface in terms of dryness, atmospheric temperature, and geological composition. All the aforementioned conditions define our design approach to the problem at hand. Besides the specific constructive and architectural guidelines behind the projects, there is one overarching principle underlying the design: to be a series to fail. Considering the challenging nature of this mission and taking into account the uncertainties associated to building Mars, we consider it extremely relevant to make all design decisions under safety criteria. This principle will be shown in all the prototypes we'll be showing now. We did 3 of these prototypes. Each one of them represents a part of the completitude in the competition that gave us access to be one of the top 30 finalists. We have 3 main notions during all the designs. First, redundancy, manifested in the constructive logic of swarm of replaceable robots and the creation of different inhabitable layers. Number 2, simplicity, expressed in simple design principle, while embedding complexity in process that does not compromise the operation's success. And 3, incrementalism, the idea that the complexity of the design comes from overlapping or addition multiple operations. We have chosen to resolve if inhabitation function, atmospheric stabilization, life support, and comfortable infrastructure through 3 different layers or boundaries, each of them specific to a function. These 3 layers are parallel with the volumetric definition made by NASA to the International Space Station. We ground that definition to the Martian soil. This is our first prototype proposal that gave us access to the next phase and to further develop the prototype ideas. We first identify different zones from recreation 1, a resting zone, a galleria to food storage and manipulation, and a work zone. In all of there will be connected in an L-shaped form. On the outside, you can see that there's also an idea for a warehouse, not quite outside in the Martian surface, but not inside the human space. Our nested atmospheric volume plan is showing that first we have the habitable volume from the inside, where humans will be using it without any external or suits. and in between we have the pressurized volume, will be like a life support milieu, and outside we will have this stabilized atmosphere that will provide protection for the robots and droids. Later we understood that make square angles for a pressurized volume will be hard for maintain structural coherence, because most of the pressure will come from inside of the settlement, not from the outside. That's why in the next two prototypes we will be facing a more curved plan. In this settlement we elaborate the idea of having different layers: one exo layer, a meso layer, and an endo layer. Each one of them will be advocated to different specific function and will be made by different techniques. Our first layer from the outside is exo layer. This layer needs to be created by autonomous robots in advance of the arrival of the humans. This needs to be done in cellular, solid, or silicate form, and will provide a general shelter to the settlement. Our meso layer is proposed to be done by an aggregation of ceramic screen modules. This will happen inside of the first layer and will be done by smaller robots. This will also be in advance of the human beings. These ceramics will help to develop the pressure volume we need to support life. Finally, our proposal for the endo layer is a plug-and-play sophisticated 3D print module that can be accommodate different tasks like archive, cook, to clean, to wash, or even computers, to provide a functional, habitable, flexible, and reconfigurable interface for the inside of the settlement. This is thought to be 2D print in a regular multi-layer and multi-material 3D printer. Most of the parts need to be printed before the arrival, but once the humans get to the base, these parts can be produced according to the necessities. Our second prototype will build upon the ideas on the first one, but with changes both in the exo layer and the internal configuration of the plan. The main idea here is to incorporate the diversity that multi-layer and multi-material printers can do for the exterior layer. We can also see that we start to incorporate the location and the landscape as a part of the strategy of the settlement. We could find a hill that can be a part of the protective strategy for the radiation, deflecting most of the high energized space particles. Our habitable zone plan is redrawn in a concentric manner. In the center of all will be an access gate that could be a technological equipment that can arrive before human beings and can also bring all the machinery to start printing the interior volume of the settlement. This access gate will also perform as our first point of entry to the habitable zone. As I said before, our nested atmospheric volume plan is shown as a concentric distribution where our point of entry to the habitable volume is the pressurized volume of the axis. In the outside, we can find the stabilized atmosphere where there is not going to be air or oxygen, but will provide shelter for the drones and equipment. In this nested layers plan, we can see that all the layers are concentric to each other, and we can see there is also some extra space in between them to provide some extra safe to fail mechanism. The endo layer is sometimes parallel to the meso layer and will provide the functions to the habitability. The main difference for the exo layer is the way that it's conceived as a structure optimization of multimaterial. It's kind of the structure that you can find for bones. We use a structural optimization algorithm to do different kind of panels, and we incorporate these panels to the exolayer structure. This allows us to incorporate some different pockets of transparency or opacity according to the different inner functions that we need to shelter. This diversity in the outer layer enables us to engage the landscape and the natural conditions on Mars. Later, we will realize that this pocket can be filled with water or ozone to provide extra shield for high energy particles. And finally, our next third prototype. This was the final product that we print for the NASA 3D Print Challenge, and will be built upon the ideas of the previous ones. Our gamble is with time. This shelter will be covered with sandust, and that sandust will help us provide extra shelter for our explorers. In this model, the habitable zone plan is also concentric with one access gate that will distribute to the different zone, and we will expand the gallery area and the recreation zone to the farming zone. You can grow your own food and see the only green field in the planet. The nested atmospheric volumes is similar to the last one, with a concentric to the core, but also will have more oxygen coming from the farming zone. We think the possibility of having a radiation blocking space between the stabilized atmosphere and the pressure volume, where we can have a layer of water. In this final nested layer plan, we can see that the concentric nature of the layers is maintained, and the main difference is we are included in the exo layer an observation window that can also provide with natural light to the settlement through the layer of water. If we see our radiation strategy, that window is set where is the less radiation exposure, and we are using the morphology of the shelter to allocate the resting areas where are most covered or distant from the sun. As we mentioned before, our rivet dome structure aims to provide an extra layer of shelter. With time, dust will settle and stop potential harms like micrometeorites or harmful radiation waves. Also, part of this dust can be used to print other things or tools that the explorers will need. In this section, we can see how we are dividing the space between the drone area and the more habitable zone, with the resting zone, current gate, and the work and food gallery. Also, we can see that our aim is to provide one point of view to the landscape and embrace the culmination of this unique enterprise that brings humankind to the face of Mars for the first time in history. Finally, we can see our 3D print model tested in the sand of the Middle East, and we can see how the sand is gathered upon it and to provide this shelter we will talk about. After all of this process, we can think the conclusion in 4 terms. One is time, second is the shape, the third is 3D print, and the last is water. We need to think about time as an ally. We need to send in advance materials. A natural phenomena like dust, radiation, or galleys could complete and improve our design. Second, we need to think about how concentric and circular shapes are better for artificial atmospheres, and also can provide a better way to complete robotic 3D printings. Third, we need to make 3D print in situ as reliable as it is in this Earth, so it can perform autonomously at a great distance. And we need to have more multi-layer and multi-material testing. And last, we need to use more water. Scientists are almost sure that beneath the surface of Mars there is great amount of water waiting to be used. We need to use it in walls or roof as a way to protect us from the radiation, in pools to use them to grow hydroponics, and also in a way to bring quality to the first settlements of the explorers in Mars.